A differential equations final. Nice! So that's what Math 267 is, differential equations. And this is an excellent vintage. Fall 22. Mwah! Beautiful, beautiful. And it was a lot of fun to write. And of course, we hope the students had a lot of fun to take. And so let's go and do it. We have 8 problems ahead, 8 things to look forward to. But of course, as always, the first thing is we should make sure to put our name, because we won't get credit if we don't put our name on it. All right, well, let's begin. Number 1, find the particular solution 3xy squared y prime is equal to y cubed plus 1. And there's initial conditions, y1 equals 2. Now this is a first order differential equation, and that has a lot more options. You've got separable, you've got integrating factor, you've got exact, and then you say, well, substitution, which really just says get it back into one of these 3, hopefully a little bit easier to do. And you have to start thinking about, well, what's the right way to do it? Now there's a small little detail here on this problem, which I just want to take a second to talk about. And it's this right here, the plus sign. Now the plus sign is a wonderful, wonderful tool. And we oftentimes talk about the plus sign is a great way to pull things apart and do them separately, but it also goes the opposite, which is it's a great way to combine things together. So in other words, when we see y cubed plus 1, are we thinking it as y cubed plus 1, or are we thinking it as y cubed plus 1? And I know what you're thinking. I just said the same thing twice, so what do you mean? Well, am I thinking of these as 2 different objects, which is y cubed plus 1, or as a single object, y cubed plus 1? And depending upon how you think of it, you might think a different approach. If I'm thinking of these as 2 different objects, then I might start saying, oh, this seems more along the lines of something where we try to get an integrating factor probably after a substitution. And in fact, you can do the problem this way. You can do this by using integrating factor. It turns into a Bernoulli problem, and who doesn't love a Bernoulli problem? And it's successful. But what if we were to think of it as y cubed plus 1 altogether? Well, now we say, oh, a new light bulb emerges. And we say, hey, I got a lot of stuff multiplying equals essentially one thing. And that says lots of multiplication. And lots of multiplication says think separable. Okay, so we're going to think separable. So we'll write this as 3x y squared, write the y prime as dy dx equal to y cubed plus 1. So now that we have our separable hat on, because every time we have tons of multiplication, separable is the way to go. If everything's multiplying, and then we separate. All right, so we'll put all the y's on the left, all the x's on the right, and hopefully life will be good. So what do we get? Well, we'll get 3y squared over y cubed plus 1 dy, okay, that's all the y terms, is equal to, now the only x terms are the x and the dx, so this is going to come over as 1 over x dx. All right, so we've successfully separated. Now after we separate, the next step, of course, is we need to integrate. So we integrate both sides. Nice. Now the right-hand side is pretty quick. Integral of 1 over x is a log x. And of course, don't forget we need to throw a constant in somewhere. Usually I like to throw it in on the right-hand side. How about the left? Well, if you look at the left, you have a y cubed plus 1 downstairs. The derivative of y cubed plus 1 is 3y squared. So this is du over u. So that means that this is a log of y cubed plus 1. And now we're like, yeah, because we are doing great. We've separated and we've integrated. Now we just need to uncomplicate, which means solve for y. Notice the answer did not say find the implicit function, which means you really should get y by itself. Okay, so let's first start peeling away the layers. We'll peel out the outer layer, which is the natural log using the exponential. And then that would give us that y cubed plus 1. And here, e to the log x would be x. And then we have e to the c, which is a constant, and that's multiplying in front. So these two c's represent constants. They're slightly different constants, but basically it's just constants all around. And I say, oh, well, here's a pretty convenient place to solve for our initial conditions. So let's solve. All right, so we bring in our initial conditions, and we say, well, what do we know? We know that when x equals 1, y equals 2. So we get 2 cubed plus 1, which is 9, is equal to c times 1, or we can just say c equals 9. All right, well, now we know what c is, so we're really close. So we say, okay, y cubed plus 1 is equal to 9x. We are almost there. We'll subtract 1. Y cubed is 9x minus 1. And finally, for the last part, get rid of the cube, take the cubed root. Because it's a cubed root, there's no plus or minus. There's only one cubed root. So y is the cubed root of 9x minus 1. And we're done. We're done. That's it. That's the whole answer. Wow. Cool. Cool, cool, cool. Now, like I said, you could have kept them separate. You could have gone down Bernoulli. You'd end up at the exact same place. So you have options. So now you're probably thinking, but which way should I go, Steve? I would say go the easiest route that you can find. And when it comes to first order, separable is the easiest way to do things. So if you're trying to think, well, let me just run through the orders, I would say separable is easiest. Exact is super easy if you can spot it. And then first order can be the most interesting. There's a couple of layers in first order. Linear first order. And but you know, at the end of the day, ultimately the key is do it in a way where you know you get the answer, because we just want to make sure you know how to solve things. All right, well, one problem down, lots still to go. Let's move on to the next problem. Number 2, find the general form of a solution for, oh my goodness, here we go, the 6th derivative of y plus the 4th derivative of y minus 86, the 3rd derivative of y, plus 252, the 2nd derivative of y, minus 200 y prime equals 0. Whew, that is a lot. There is a lot of stuff going on here. Okay, so how do we proceed? Now this is a great question. Like, how do we go about making progress in this problem? Well, there's more to say, right? In terms of d notation, this can be rephrased as finding the general form of a solution for d minus 2 cubed, d squared plus 60 plus 25y equals 0. You know what? They just told us how to do the hardest part, if we can unravel what this is saying. Now, remember what d stands for. So d stood for take derivative. And so we have this lovely d notation. So for instance, if I had, let's just do a simple example, y double prime plus 5y prime plus 3y equals 0. Well, this would become d squared y plus 5dy plus 3y equals 0. Or if you like, d squared plus 5d plus 3y equals 0. Right? That was the d notation. Now, how does that help us? Well, when we're looking for, here we have constant coefficient, linear, homogeneous, all the best words. Then what we were going to do is we're going to form the characteristic polynomial. Come back here. What's the characteristic polynomial? Well, with the derivatives, whatever the derivative is, you replace it with a power of r. We're looking for roots. R squared plus 5r, no derivative, plus 3 equals 0. Now take a look between these. What do you see? It's the same polynomial, except here we have d's with a y in the end, and here we just have r's. So r was associated with taking derivatives. So once we have things in d notation, we can jump to r notation and actually jump back. So what does that do? Well, it tells us that our characteristic polynomial is r minus 2 cubed, r squared plus 6r plus 25 equals 0. So we need to find the roots of this polynomial. Now, some of the roots are pretty easy, and they're just sort of freebies. So let's talk about the freebies. First off, r. Well, that would correspond to r equals 0. How about r minus 2 cubed? Well, that would be r equals 2, but notice how we have that cubed. So that says we have repeated roots. And then we have this r squared plus 6r plus 25. Now this one, we're going to work a little bit. We're going to do a little bit of completing the square. So this would be r squared plus 6r. Okay, 6 divided by 2 is 3, so I want to add 9, and then add 16 more. So this is r plus 3 squared plus 4 squared. All right, now, if you're familiar with completing the square, and in terms of complex roots, this means that it's a complex root, namely negative 3 plus minus 4i. If you're not convinced about that, and you don't have to be, you know, as the saying goes, don't take my word for it. We can do other things. Here's an alternative. We could throw it into the quadratic formula, which is perfectly allowed. Negative b plus minus square root b squared minus 4ac, so that's minus 100, all over 2a. Well, negative 6 over 2 is negative 3. 36 minus 100 is negative 64. Square root of 64 is 8. So what we have here is we really have plus or minus 8i over 2, which is that negative 3 plus minus 4i. All right. So quadratic formula, or know how to use completing the square, either way, we get the roots. So in summary, so far, we have one root of 0, 3 roots of 2, and a pair of complex roots. All right. Well, now we've worked through, started with the differential equation, gone to that characteristic polynomial, gotten that roots. The last step is how do we go back and translate roots to answers? Well, that would be just work through one root at a time. The root of 0, well, that would be e to the 0t, and which is just a constant, so we'll write a. So this is the root of 0. How about the repeated roots? Well, we work our way up. So a root of 2 would be e to the 2t. So e to the 2t. Then the second time we have a root of 2, that's going to give us a second e to the 2t. Well, I can't use it again because it doesn't give me anything new. So we bump. All right, so we add c t e to the 2t. Now I go to my third root of 2. Again, e to the 2t, but I've already used that. Bump, well, I've already used that, so bump again. And we'll get constant t squared e to the 2t. So this part right here goes from our repeated roots. But we're not done yet because we still have our complex roots. Now remember, complex roots are going to come in pairs where we have sines, cosines. The real part goes into an exponential, and then the imaginary part goes into the sines and the cosines. So we see the real part, so we say, okay, capital E, e to the minus 3t, cosine of 4t, right? The minus 3 into the exponential, the 4 into the sine or cosine. And then, of course, its pair, f e to the minus 3t sine of 4t. And so we get that. That's those complex conjugate pairs give us those two. And now we are done. Because we wanted the general form. And we found it. Now there is one quick check to see if at least we're in the right ballpark, right? Which is, how many functions do we have? 1, 2, 3, 4, 5, 6. What's the degree? 6. It's the 6th order polynomial. A 6th order differential equation, which becomes a 6th order polynomial. So we should have 6 functions, and we do. Life is good. All right, and that's it. That's all there is. I know, you're like, wow, can't we do more? Well, yeah, we've got a bunch more problems still. But for this one, we're done. On to the next. Number 3, find the general form for solutions to y double prime plus y equals 2 secant x. Aha! Wow! All right. Well, where are we at? Here we have constant coefficient, linear, non-homogeneous. And we look at this function and say, oh, is that a nice function? Secant x? Unfortunately, no. It's not exponential, or whole powers of our variable x, or sines and cosines. It's secant. So what does that mean? Well, it means that we are forced into a particular strategy. We have to go with variation of parameters. All right, so that's our only option. But that's okay. All right, so how does variation of parameters work? Well, we start by looking for the solutions to the homogeneous part. So that's where we start here, because they didn't give it to us. Now, if they had given it to us, we would really like them a lot more. But if they didn't, that's okay. We still like them, I guess. Y double prime plus y equals 0. Turn into the polynomial r squared plus 1 equals 0. Those turn into roots r equals plus minus I, which in turn gives us that for the homogeneous part, which is the complementary solution. Well, that would be some constant times cosine and some constant times sine. There's no real part, so there's no exponential. And then we have 1 times I, so there's 1 times t, 1 times t. Okay, so these are important. And they're going to show up. We might call these, depending upon notation, we could call this one here our first function, and we could call this one here our second function. Now, the next piece that we're going to need is we're going to need the Wronskian. So the Wronskian, remember, it's going to be a function. And the way you find it is you take the determinant where you have y1, y2, the functions, y1 prime, y2 prime, the derivatives. So we would have cosine, sine, negative sine, cosine. Take the cosine squared, subtract negative sine squared. And what do we see? Well, we get cosine squared subtract negative sine squared. Aha! Nice Wronskian. That is a very, very nice Wronskian. I like that Wronskian. All right, so we've made progress. We found our pieces of our homogeneous. We found the Wronskian. And now we say, okay, we just need the formula. If only we had a formula sheet. Well, aha, I happen to have one. And on this formula sheet is variation of parameters. Now it uses x's instead of y's, but that's all right. Here, the x1, x2 is what we were calling y1, y2. There's just one little thing we should point out. What is the f? Well, the f is this part right here. Now, I want to be ever so slightly careful because I want to make sure I don't lie to you. There is one thing you have to check before you call it f, which is you look at that y double prime. and you say, what's in front of it? If it's 1, the right-hand side is f. If it's not 1, make it 1, and then the right-hand side is f. All right, but with that in mind, we can now copy this. So I'm just going to put this to the side, and I'm going to write down our formula here. So the particular solution, because we already got the complementary solution, we have minus y1 integral y2f over the Wronskian y1, y2. And then we're going to add y2 integral y1f over the Wronskian y1, y2 dx. Okay, so just copying off the formula sheet, just changing a few letters, and we're ready to roll. Okay, so we're putting in all the pieces. So we have minus y1. Well, that's minus cosine t integral sine of t, whoops, not t, x. Why have I been writing t's, x's? I am so sorry about that. It's easy for me to get caught up. Sometimes things are t's and sometimes they're x's. I apologize. There we go. There we go. Don't want to lose any silly points. Okay, so back to where we were. So y2 times f, so times 2 secant x over the Wronskian, which is 1, plus, okay, y2, which is sine of x, integral y1, which is cosine of x, and then times f, which is 2 secant x, over 1 dx. All right. Now, does anything simplify? Yes, a lot. For example, secant is 1 over cosine. So cosine times secant just becomes 1. The 1 we can ignore because that's just 1. Now, sine and secant don't cancel, but they combine. So it's sine times 1 over cosine, that's sine over cosine, also known as tangent. So we have minus cosine x, integral of tangent x. And the good news is we know the integral of tangent x, or at the very least, we know where to look. Integral of tangent log secant. Good. Okay, so it's minus cosine of x log secant of x. And then it's plus sine of x. And here, the integral of 2 would be 2x. Whoops, I forgot the 2 over here. There we go. It all fits in. And great. Now, we could put a plus c if we wanted to, but this is, we're just after the particular for right now. And if we add the c's, we'll get the general. So how do we put it all together? What's the final answer? Well, because we want the general, so we have to combine these two. So our answer is, we have some constant cosine x, some constant sine of x, minus, all right, this has 2 cosine x log secant x, and then plus 2x sine x. And that's the answer. And we're done. Now, could we do things? Absolutely. We're great at doing things. For instance, this minus can go into the log, and instead of minus log secant, it could be plus log cosine. But it's the same thing. It's the same thing. And at this stage, we're pretty happy because we found an answer. So remember, if it looks terrible over here, well, probably variation of parameters. The other thing to watch out for is maybe this is a nice function, but the coefficients on this side, oh, now they're terrible. If so, really to use method of undetermined coefficients, it's very, very narrow. Have to have constant coefficients for the left-hand side. Right-hand side has to be a pretty function. So if you have messy coefficients on the left-hand side, messy function on the right-hand side, any combination of those two, you've got to go with variation of parameters. So it's good to know we have something which will work. All right. Whew, that was a workout. But we still have a lot of problems left, so let's keep going. Let's get ready to do number 4. Find the particular solution for x prime is 6, 4, minus 1, 2x, with x of 0 is 3, negative 2. All right, so what do we see here? We see matrix, systems. And whenever we have matrix, the very first thing we're always going to do is find eigenvalues. Because depending on what the eigenvalues are, there's different roads to go down. So there's the distinct real, repeated, and complex. Each one of them has a slightly different way to approach it. Let's find out where we are. So finding the eigenvalues, we're going to set 0 equal to the determinant. We take our matrix, let's call this A minus lambda I, which means we subtract lambda on the diagonal. All right, good. So multiply, subtract, multiply. So we have 6 minus lambda times 2 minus lambda, subtract negative 1 times 4. Well, this will become lambda squared. All right, we'll put that down. We have minus 6 lambda minus 2 lambda. Minus 6 minus 2 makes minus 8 lambda. Then we have 12 plus 4. Yes, see, 6 times 2 is 12. Minus minus makes plus. So 12 plus 4 makes 16. Okay, now, spoiler alert. Your teachers like you. They're going to give you nice numbers to work with, which means this will factor. Or, quadratic formula, it'll get complex, but it'll still be nice numbers. If they're not nice numbers, something happened. Hopefully it's not that they weren't paying attention, but something happened. Okay, so does this factor? Yes, it does. Looking for two numbers that multiply to 16, add to negative 8. Well, it's lambda minus 4, lambda minus 4. Of course, good to check. Lambda squared, yes. Minus 4 lambda, yes. And plus 16. Now, what does this mean? It means our eigenvalues are 4, 4. Repeated eigenvalues. When we see repeated eigenvalues, in our mind, emotionally, we are like, yes, we are in our happy place. It's a happy place to see repeated eigenvalues. And I know what you're thinking, why is that a happy place? Because we have a shortcut, a tool that reduces our work. And so that's why we're happy. And if you grab your formula sheet, assuming that they're nice enough to give you a formula sheet, you'll see that there's this nice little formula that says e to the at is e to the lambda t times the identity plus a minus lambda I t. This formula is when we have a 2 by 2 with repeated eigenvalues. Well, we have a 2 by 2. We have repeated eigenvalues, so we can use it. So, in particular, we say, in our case, lambda is the 4, so e to the 4t. The identity, that's the 1, 0, 0, 1. It just, you think of ones down the diagonal. Now, a minus lambda I, well, just come here and put in lambda equals 4. So that would be 2, 4, minus 1, minus 2 times t. Or if you write this out by, well, combined together, let's say it that way. 1 plus 2t, 4t, minus t, 1 minus 2t. All right, good. Now, that's not the answer. But the thing is, once we have the exponential matrix, we can get the answer. Maybe it says, find a fundamental matrix, and then it is the answer. Or maybe it says, find a general form. Say, first column, second column. The columns are the solutions. Or maybe, just maybe, it'll give us initial conditions. And with initial conditions, how do you find the final answer? Well, you have that x of t is e to the at x0. Well, we know what e to the at is. It's right here, so we just copy that. So times x0, 3 minus 2. All right, so we have e to the 4t. So we're going to multiply by 3. So we're going to get 3 plus 6t. And then we're going to have minus 8t. Yes, right. Doom, doom. Then the next row we'll have minus 3t and minus 2 plus 4t. Do, right? Matrix multiplication. Know how it works. And finally, we just clean it up. So we have 3 plus 6t subtract 8t, so that makes 3 minus 2t. And here we have a minus 2 and a minus 3t plus 4t, which makes a single plus t. And we're done. Don't forget that e to the 4t in the front. Life is good. Life is good. So remember, repeated roots is happy because it gives us e to the at, and off we go. Off to the races. Life is good. Life is wonderful. Ah, I hope we see another one of those. I like those. All right. But for now, on to the next one. Number 5. Woohoo! Okay. Find e to the at, where a is the matrix, in the differential equation x prime equals 1, 2, minus 1, 4. Okay, so in other words, we're saying this part is a. All right. Now, it doesn't have to have a differential equation. We could have just said find e to the at, but we're going to use the differential equation to help us. So, any question where we have matrices involved, find the eigenvalues, right? All right, so here we go. So we're set 0 equal to determinant 1 minus lambda, 2 minus 1, 4 minus lambda. All right, so that's going to be 1 minus lambda times 4 minus lambda, subtract minus 1 times 2. What will that be? Well, we have our lambda squared. All right, that's good. Minus lambda minus 4 lambda makes minus 5 lambda. Then we have a 4 plus 2, right? 1 times 4, and then minus minus makes plus 2. So plus 6. All right, lambda squared minus 5 lambda plus 6. Does it factor? Yeah, it factors. How does it factor? Well, we need two things that multiply to 6, add to negative 5. Lambda minus 2, lambda minus 3. Again, check. Got your lambda squared. Minus 3 lambda, minus 2 lambda. That's good. And your plus 6. So, our eigenvalues are 2 and 3. All right, now, we're not quite in our, oh, that's beautiful, but we're like in our, you know what? We'll work with it. It's something. It's something we can work with. Okay, so what are we going to do? Well, let's use, let's now find our eigenvectors. Okay, so here we go. For our eigenvectors, we'll do lambda equals 2. So if we have distinct real eigenvalues, we go and find our eigenvectors. We have to find both. So what you do is you say, all right, put in your lambda into here. So we'd have a minus 1, a 2, right, 1 minus 2 is, whoops, minus 1. I said it, but I wrote the wrong thing. A minus 1 and a 2. Okay, so minus 1, 2, minus 1, 2 times something equals 0, 0. And the question is, what's the something? Well, there's lots of choices. Just don't choose 0, 0. And what I like to do is go backwards and flip a sign. So I'd put 2, and I'll flip the sign. Minus minus 1 make 2, 1. So there we go. 2, 1. Done. All right. So that's our eigenvector. And now let's do similar. Lambda equals 3. Okay, so 1 minus 3, that's negative 2. 2 minus 1. 4 minus 3 is 1. We need to multiply this by something and get 0, 0. All right, can we think of something? Well, yeah, 1, 1. Yes? Right. You know, again, write that second row backwards, flip a sign. So these are our eigenvectors, which is good. So we've gotten our eigenvalues, and now we have our eigenvectors. So how do we use all of this to get to e to the at? Well, there's a couple ways to do it, but the easiest way is we're going to use a formula. And there's a formula given on the equation sheet, at least if we're nice, and we are. There's a formula that says the following, namely e to the at is this fundamental matrix phi of t, and then we multiply that by phi of 0 inverse. So what we'll do is, this is our goal. We're going to build up phi of t. And the way we get to phi of t is we form our solutions. So we're going to take eigenvector times eigenvalue. So in particular, if this was our differential equation, then we would say that our general form looks like x is some constant e to the eigenvalue t times eigenvector plus some constant e to the eigenvalue t times some vector. So our phi is the two solutions become the two columns. So the first solution is 2e to the 2t, e to the 2t. The second solution, e to the 3t, e to the 3t. Now you might be saying to yourself, how do I know which one goes in which column? And the answer at this point is, it doesn't matter. It won't make a difference. We'll fix that. And it fixes itself automatically in the next few steps. Okay, so the next thing to do, we're going to find phi of 0. So plug in t equals 0. The nice thing is e to the 0 is 1. So we're going to get 2, 1, 1, 1. And now we need to find the inverse. Okay, so let's remind ourselves what the way to find inverses are. All right, we'll do it down here in the corner. So if I'm after a, b, c, d inverse, that's 1 over the determinant, so AD subtract BC, and then you flip the diagonal entries, flip, and you flip the signs on the off diagonals. Now this is for a 2 by 2, but that's as far as we want you to master. So if we apply this phi 0 inverse, well, the determinant would be 2 minus 1. So 1 over 2 subtract 1. Flip the diagonals, 1, 2. Change the sign on the off diagonals, and there we go. Now, if you're paranoid, you can check. The way you check is you multiply these two matrices together, and what should you end up with? You should end up with 1. Well, you should end up with the identity, 1, 0, 0, 1. All right. So we won't be paranoid because, well, we only have a little bit of space left because we'll have to put it all together. All right, so here we go. Wrapping it up, we get the following. We have e to the at is, we write down our phi of t again. So 2e to the 2t, e to the 2t, e to the 3t, e to the 3t, times our phi 0 inverse. Well, of course, in the front we just have 1. So we're going to multiply that by 1, minus 1, minus 1, 2. And matrix multiplication, so 2e to the 2t, subtract e to the 3t. So on the rows, down the columns. Rows on the first, columns on the second. So 2e to the 2t, subtract e to the 3t. And then minus 2e to the 2t plus 2e to the 3t. minus 2e to the 2t plus 2e to the 3t. Then second row, first column, e to the 2t minus e to the 3t. All right. And minus e to the 2t plus 2e to the 3t. And we have our e to the at. And that's what we were after. And so we're done. We're done. Woohoo! We did it! So just recapping what happened. We were after an exponential. We figured out we had distinct eigenvalues. So we found the eigenvectors, which helped us find the solutions. The solutions, we made a fundamental matrix called phi of t. Each column is its own solution. And then we said e to the at is basically a fundamental matrix. We just have to correct it, which is where this phi 0 inverse comes from. So we computed phi 0 inverse, set up the computation. E to the at is phi of t, phi 0 inverse, carried out the computation, put it in a box, gave ourselves a little emotional high five. We're very happy. Whew! And on to the next problem. Number 6. For each Laplace transform, so there's a bunch of them, fill in the box with the label corresponding with the correct answer among those listed on the right. So they gave us a whole lot of options. Now, there's only going to be one correct answer, so we're definitely not going to use them all. And it's possible that one might get used more than once. It's highly unlikely, but of course, they can be sneaky. They are known for being sneaky, those math teachers. They're just waiting. They're just waiting to see if we're paying attention. All right, so let's go through it. Now, the nice thing is we don't have to do any justification for them, but of course, we want to make sure we understand it. So let's see if we can figure this out. Okay, so suppose we wanted to do the Laplace of t e to the t. Now, this is going to combine two facts. So we should see, I think I still have a nice formula sheet here. Yes, I do. So there's a couple of things. I know how to handle Laplace t, and I know that when I multiply something by an exponential, it's a shift. So I could say, aha, I can use the fact that I know Laplace t from the formula sheet is 1 over s squared. And so the Laplace of t e to the t, well, this is going to shift. And it's really t e to the 1t. And so what's the shift? Well, I'm going to replace s by s minus what's in front of the t upstairs in the exponential. So it's going to become 1 over s minus 1 squared. So to be clear, because, we want to be clear, this one here is coming from this one here. So the 1 in front of that t in the exponential becomes that minus 1. So we're looking for a 1 over s minus 1 squared. Aha! There we are. So L. All right, cool. Now our next one. Okay, we have e to the t u of t minus 1. Now, again, we know multiplying by e to the t shifts everything. Well, what about if I just do u of t minus 1? Do we know how to do that? Well, we check. Say, well, yeah, it's on our formula sheet. So, in fact, right there, u of t minus 1 would be e to the minus s over s. Okay, so Laplace of u of t minus 1 is e minus s over s. Now, we're multiplying by e to the t. What is that going to do? So what does that do? Well, it's the same shift we just talked about. So if I have Laplace of e to the t, u of t minus 1, I'm going to shift all of my s's. So everywhere I see an s becomes in s minus 1. S minus 1. And again, just to emphasize, so we get the hang of this, these ones here come from this one there. All right, so do we see an e to the minus s minus 1 over s minus 1? Well, not quite in that form, but of course we know we're looking for an s minus 1 downstairs. And, well, okay, does that work? Okay, well, if you distribute the minus through, that becomes minus s plus 1. Yeah, that works. It's d. That's what we're after. Good. So now d. LD. Not a lot of words that start LD. Well, okay, missed opportunity. We're not going to be spelling any words. But that's all right. We don't have to spell a word. All right, on to our next one. Okay, t minus 1, u of t minus 1. Now, this is good news for us because I want to come back to the formula sheet. It has the right form. You have that step function, that on-off switch. And then our function is in terms of that t minus 1, right? T minus 1, t minus 1. So what happens is, we're going to add an e to the minus s, so we know our answer has e to the minus s times a little bit. Now this little bit would be the same thing as if we just did normal f of t. Okay, so we say, okay, so if we're doing Laplace of t minus 1, u of t minus 1, we know this will get e to the minus s. So that's only coming just from that part right there. And then this other part, well, what's going to happen is we're going to say, think of this as just the function t. It's what would the function be if there weren't the shift? And the answer is t. Okay, well, how does t go? Well, we know how t goes. We did it before. So that's 1 over s squared. So we're searching for e to the minus s times 1 over s squared. Is there anything like that in our list? E to the minus s over s squared. Oh, there is. It's right there. E to the minus s over s squared. Okay, so that's an e. Interesting. All right. Well, let's go to our next one. All right. Well, here we go. The integral 0 to t of tau e to the tau, d tau. Now, here, I like to think this is a layered problem, right? There's the tau, e to the tau, and then you integrate. And there's a nice rule. You're probably thinking, there's always a rule, Steve. You keep pulling out all these rules. We're integrating a function. So if you integrate a function, you add a divide by s. Now be careful, there's convolution, which is different from just integrating a function. If you don't have a t minus tau showing up, it's not a convolution. It's a straightforward integral. So we say, well, do we know how to do just t e to the t? Is that anywhere on here? Do we know how to do that? Well, the good news is, yes. T e to the t we know is L. So we say, okay, find L. The integral says now add a 1 over s. So it's 1 over s times 1 over s minus 1 squared. So we scan. We say, okay, I'm looking for a 1 over s times s minus 1 squared. That's going to be O. All right, so we found it. Oh, good. Ladio. One more. Okay, so for our last one, okay, so now we have an integral, 0 to t of t minus tau e to the tau. Here's where we talked about convolution. Okay, so we have convolution. Let's go back to our formula sheet, because we have a t minus tau and tau. It doesn't matter which one comes first, doesn't matter. So when we have one part is t minus tau, one part is just tau, do them separately and multiply. Okay, so what do we have? Well, let me move this up. So the Laplace of the integral 0 to t, t minus tau e to the tau d tau. Well, the e to the tau, okay, we can do that part. That would become 1 over s minus 1. This part right here, so this is our function e to the t, becomes 1 over s minus 1. This right here, we're really thinking this as t. So another way to write this, by the way, is that we're taking the convolution of t and e to the t. So this is the convolution. So these are our pieces, t and e to the t. So we say, okay, so this is the t part. So that will give us 1 over s squared, because we mentioned that before. So now we're looking for 1 over s squared times s minus 1. Well, do we have a 1 over s squared times s minus 1? Well, we better be on our list. And it's right there. So that makes an n. L-D-E-O-N. Ledion. Haha. Yes. Well, we are almost Ledion with this test. Only 2 more problems. Woohoo! Yay! All right, so let's finish those last 2. And then we'll be done. Yeah. Number 7. A spring mass damper system is set up with a mass, m equals 1, damping constant 3, spring constant 2. Initially, the spring is at position x of 0 equals 4, and the velocity is 0, x prime 0 equals 0. And then at time t equals 6, a pulse force of 7 is applied to the system, which means that the external force is 7 delta t minus 6. So it's a pulse force. That means it's a quick, and then only that 1 instant. So that's a delta function. And then we have a 7. All right, so set up and use Laplace transforms to solve the differential equation modeling this system. All right, so first off, we have a spring mass damper system, or just spring mass sometimes we call it. So we have our mx double prime. So that's our mass times acceleration. Our damper constant, which comes with velocity, because the damper, it scales with velocity. So the faster it goes, the more it tries to slow you down. And then we have the kx, and that's the Hooke's law coming into play, and that's your external force. All that together. Okay, so we just fill in our pieces. So we have our mass is 1, which is convenient. C is 3, so 3x prime. K is 2, 2x. Our external force is the delta function, t minus 6, because it tells us what it is. And we'll throw in some initial conditions. X of 0 equals 4. X prime of 0 equals 0. All right, so there we go. So this is the word part of the word problem, with the translation from text to differential equation. Now that we've done the word part, the next step is to say, okay, we need to solve it. And we're not going to just solve it, we're going to solve it using Laplace transforms. Now, how do we know we're using Laplace transforms? Because they told us to. we know we want the points. And one of the things that we know is if we don't follow instructions, we don't always get all the points. In fact, we'll usually lose points if they're very explicit and we go against their directions. So how do we solve with the Laplace transform? Well, we start by taking the Laplace transform of both sides. So Laplace transform of x prime, 3 Laplace transform of x prime, 2 Laplace transform of x is equal to 7 Laplace transform of delta t minus 6. Now, for the Laplace transform of x double prime, we have a formula for that. It's on our formula sheet. As for x prime, the only thing is instead of x we have f, but okay, we can adapt. We're adaptable. So, using our formula sheet, this is s squared capital X, subtract s, x of 0, subtract x prime of 0. Okay, that's the first one, plus 3. Now, Laplace of x prime will be s capital X subtract x of 0. Again, formula sheet. I'm not putting any thought into this. This is just formula sheet. Plus 2 capital X equals 7. And delta, again, what am I going to use? It's the formula sheet. Yes, there it is. The delta function's on our sheet. So that's 7e to the minus 6s. All right, so we now start cleaning up, which means a few things. We first off plug in what we know. For example, x prime 0 equals 0. That's good. X of 0 is 4. All right, so we put 4s here, and we'll just keep track of those. And now we're going to gather. What has the x's? Well, there's an s squared, a 3s, and a 2. And those are the x terms. The other stuff moves across. So there's a 4s. It's a minus 4s, but it comes across as a plus 4s. There's a minus 12, which becomes a plus 12. And a plus 7e to the minus 6s. All right, good. So you might notice s squared 3s2, these coefficients 1, 3, 2 look a lot like these coefficients 1, 3, 2. Coincidence? No, it's not a coincidence at all. It's an anti-coincidence. I don't know what you call an anti-coincidence, but that's what it is. And so we say, okay, cool. So now we're almost there. Let's think about this. Now, s squared plus 3s plus 2, what does that become? That's s plus 2s plus 1, isn't it? All right, two things that multiply to 2, add to 3, s squared, yeah, s, 2s, good. So what does that mean? Well, what that means is we have a pretty big damper on our spring. So when you see no complex roots, that says the damper is so strong, it's overpowering the spring. And so it's no longer springy, it's, that's the difference. Okay, so no worries, that's okay. So what do we get? This leads to the following. Capital X is 4s plus 12 over s plus 2 times s plus 1 plus 7 over s plus 2 s plus 1 e to the minus 6s. You might ask, why did you separate these two? And the answer is, I separated because of that e to the minus 6s. So we're heading towards partial fractions. Partial fractions do not mix with exponentials. Partial fractions only work polynomial over polynomial. All right, so we have two pieces here. The 4s plus 12 over s plus 2 times s plus 1, and the 7 over s plus 2 times s plus 1. We're going to have to do them separately. But that's okay, because these are the nice kinds of partial fractions. The kind of partial fractions we could introduce to our family and not be terribly embarrassed about. All right, we'll start with the 4s plus 12 over s plus 2 times s plus 1. That's something over s plus 2 plus something over s plus 1. Clear the denominators. 4s plus 12 is a times s plus 1 plus b times s plus 2. Make good choices. If we choose -1, that knocks a term out. Minus 4 plus 8 is, minus 4 plus 12 is 8. That's when I get too far ahead of myself, is 0. B times 1. So 8 is b. Good. And s equals -2. You got minus 8 plus 12, which is 4. You'll get 0. You get 0 here. And here you get minus a. So 4 is minus a, or, using very fancy technology, a is minus 4. All right, so that's 1. What's the other partial fractions look like? Well, that's going to be the following. So you get 7 over s plus 2 times s plus 1. Looks like something over s plus 2 plus something over s plus 1. Clear your denominators. So 7 is some constant times s plus 1 plus some other constant times s plus 2. And we're going to feel a little bit of deja vu because it's the same downstairs, but we still go through the process. So plug in -1. We're going to get 7 is 0 plus d. So d is 7. Plug in -2. We're going to get 7 is negative c, and then that's going away. That's 0d. So 7 is minus c, or c is minus 7. All right. Well, we're running out of space. I hope that means we're also running out of problem. Fingers crossed. That's what it means. So let's see where we're at. We have x. Using our partial fraction decomposition, we can rewrite this, expanding it out. We're going to have the first piece is going to become a -4, 1 over s plus 2, and then a +8, 1 over s plus 1. And then we have that 7. Well, of course, I can just pull the 7 out, and we have that e to the -6s. And then when we pulled out 7, because they're both c and d have 7, what's left? Well, we have c, which is a -1 over s plus 2, and d is a +1 over s plus 1. All right, so we're in the home stretch. We started with our differential equation, took the Laplace transform of both sides, grouped, rewrote it, used partial fractions to break things up, because partial fractions is very common when we're doing our Laplace transforms. We kind of anticipated at some point. Now we've expanded, and we're ready to talk about our pieces. Okay, so let's talk about our pieces. 1 over s plus 2, well, that would be e to the -2t. Think of it as s minus -2. So that -2 from that s minus -2. Over here, 1 over s plus 1 is e to the -t. It's going to be similar on this side. We have e to the -2t and e to the -t, except here, this says, oh, shift. I know. What's the shift? Well, -6 says u of t minus 6, and we're going to replace t by t minus 6. And what I mean here, these t's are going to become t minus 6. So our last thing is to write down the answer. So our solution, x, is -4 e to the -2t plus 8 e to the -t plus 7 u of t minus 6. And we're going to get minus e to the -2 t minus 6 plus e to the minus t minus 6. See how we took these t's and put t minus 6? Also notice our generous use of parentheses, so we didn't make any mistakes. Yes, parentheses are very, very nice. They're wonderful tools, and you should use them extensively. They'll save points. Someday, you'll look back and say, oh, I'm glad I was using my parentheses. All right. Well, whew, that was a good workout. And but it was good to do it. Good to go through and carry out the whole process. Okay, well, that means there's only one left. Oh, we're almost at the end. All right, let's do it. Our last problem. Our last problem. Woohoo! We're almost done. Yes. Okay, so here we go. We're given that y is the series solution, so it's a sum ck x to k, And so solution to the differential equation, y double prime plus 3y prime minus 2xy equals 0. And we have some initial conditions. Y of 0 equals 6, y prime of 0 equals 2. And we're asked to find C0, C1, C2, C3. Okay, so, well, good news. What aren't we asked to find? We are not asked to find the recurrence relation. How do we know that? It doesn't say that. And so we're like, well, what does that mean? It means we say, look, we just need just enough. So what is just enough? Well, because it's second order, we have two initial conditions, and the two initial conditions give us our first two terms. So C0, C1 are coming from the initial conditions. All right, that's great. C2, well, that's going to come from our constant coefficient, and C3 is going to come from our coefficient for x. And so we don't have to go too deep into our solution to grab what we need. So we're going to just do just enough. Just enough. All right. So, well, let's use our initial conditions really quick. C0, y of 0 is 6. And C1 is y prime of 0, which is 2. I should say C0 and C1 are special. Once you start hitting C2, you have to add some extra scaling factors, but we normally don't ask you to do third order, and we definitely wouldn't ask you to do it on an exam. So here we go. So since I'm not after everything, I'm not after recurrence, I'm just going to focus on the beginning. So C0 plus C1x, C2x squared, C3x cubed. And I don't need to worry about anything else because I can stop at C3 because that's all I need to get to. Y prime, well, that's C1, 2C2x, 3C3x squared. Y double prime, 2C2, 6C3x. All right, so I now have my pieces, and I'm going to plug these into my relationship. And I really don't have to grab too much. I just have to grab just enough to get us going. So for y double prime, I'll have 2c2 plus 6c3x and dot, dot, dot. Now, before I go too much further, remember what I said. I need the constant term to get me c2. I need the x term to get me c3. So the x squared and above, I don't need. So keep that in mind as we do our next pieces. Plus 3. So I'm going to have y prime, c1, 2c2x, and then dot, dot, dot. Because I don't need the x squared term. That's not going to help me. And now minus 2x, and I plug in for y, c0 plus dot, dot, dot. Now you might say, whoa, whoa, Steve, you're being very aggressive here. Well, see that x? We're already up to a constant something times x. So if I had it an x term, c1x would be up to an x squared. So that x says I only have to go this far. And all of that equals 0. Okay, so grouping our coefficients. 2c2, 3c1. Those are our constants. There's no constant term there. Plus, now coefficients of x. 6c3, 6c2, minus 2c0x. And other stuff. Other stuff I don't need to worry about. Why? Well, because I have two pieces of information. I know that the 2c2 plus 3c1 has to equal 0, and I know 6c3 plus 6c2 minus 2c0 has to equal 0. And how do I know that? Because I have to end up with 0. I have a big polynomial. The only way a big polynomial can equal 0 is if everything is 0. So that's how I know these pieces are 0. All right, so let's start with this first piece. So 2c2 plus 3c1 equals 0. But do we know one of these. We know C1 is 2. So 2C2 plus 6 equals 0, because I replaced C1 by 2. Well, that says C2 is subtract 6, divide by 2, is negative 3. Okay. Now we come here. We know that 6C3 plus 6C2 minus 2C0 equals 0. We just found C2. So that becomes 6C3. 6 times minus 3 is minus 18. We also know C0. It's up here. So that becomes minus 12. Okay, minus 18 minus 12, that would be minus 30. So we could say, aha, that says C3 is 30, because it comes across as a plus 30, over 6, which is 5. And so, putting it together, we get our C0 is 6, C1 is 2 from initial conditions. Then grabbing the constants and comparing, C2 is negative 3. And grabbing the coefficients of x and comparing, C3 is 5. 6, 2, negative 3, 5. Our coefficients that we were after, we found them. Life is good because we're done. Woohoo! Yes! Ah! All right, what a test. What a great test. And I hope that you've got all this down. And of course, if you don't, well, you have some time. Sometime. All right. Well, thank you for joining me. Hope you have a great day. Hope you have a great test. And maybe I'll see you again. Bye.